Hi, everyone. Welcome. A little bit more about my background. So I worked most of my career on netlist optimization algorithms, trying to improve the Fmax and logic utilization of your designs. But the last few years, I've become more focused on usability features because I really feel that if we can get the right analysis tools to you, then that allows you to complete your design development faster. So that's what I'm going to talk about today. So first, we have 3 focus areas in Quartus that we're working on to help getting the designs completed faster. So first is faster. We try to make the tools faster, faster compile time, faster simulation time. Second is IPs. So we have a rich IP portfolio across a lot of different markets that help you create your designs faster. And then third is ease of use, which goes from example designs that you can start your design with, or to usability features like new analysis tools that help you to analyze what happens with your design in our tool. So the agenda today, I'm going to take you on a tour of some of the improvements that I think are important that we did in the last few releases, and also some new features that we introduced that I'm very excited about, and I hope you will all try to use. I'm going over 3 sections: getting started faster, faster design closure, and insight through simulation and debug. So let's start with getting started faster. Well, the first thing you need to do to get started is install Quartus. And we made the process to install it much simpler and faster. You can just go to the download center, and from there you can choose the Quartus and the version that you're interested in and the platform you want to install it on. And that takes you to the installer, which lists all the components that you can install. And it's just easy checkboxes to mark the ones that you want. For example, the software itself, of course, but also the simulator, the devices that you're interested in, and then any add-ons that you would also like to have. And then it's just a matter of providing the path where you want to install it, and you click download and install, and off you go. We also provide no-cost licenses if you have for the Agilex FPGA E-series. You get a no-cost Quartus license, but also many IPs, like a NEOS 5 processor has no-cost licenses. And those are now very easy to get from Quartus with one-click licensing on demand. So another part of getting started quickly is IPs and design examples. So we have IPs in a lot of different market segments: network interconnect, communications, memory and storage, compute interconnect, embedded processing, algorithmic and signal processing, and video and edge. And all these IPs are correct by construction. It means we've already proven that they are working. So all you have to do is use them, and you don't have to create them from scratch. We also have example and demo designs that kind of show you how you can easily instantiate these IPs. So moving on to faster design closure. So on the left is a flow diagram of how you would take your design through a compile in Quartus. So you start with your Verilog and VHDL and your timing constraints and other assignments. Then first stage of the compile is analysis and elaboration, which takes the Verilog and VHDL and converts it to a netlist of primitives. And then second, synthesis takes this netlist and optimizes it for logic depth, Fmax, also just logic utilization. And then at the end of synthesis, the netlist is mapped to primitives that can go on the chip. And the fitter will take this netlist of primitives and places and routes it. So it places all these primitives at locations on the chip and routes all the connections between them. And then while it does that, of course, it tries to meet all your timing constraints as much as possible, and try to reduce the logic utilization, power, and those kind of things. So a lot of optimization goes on during that stage. And then finally, you can use the analysis tools to basically look at how the compile went, whether your design is meeting timing or maybe you still need to work on it. Typically, this is not done in one iteration, like your design will not meet timing the first time, or maybe there's some other constraints that are not met. So you make some changes to the assignments, timing constraints, or maybe to the RTL, and repeat this process until you're done. So to make this whole process faster, we have made improvements that lead to faster and fewer iterations. So first of all, faster compile time, better Fmax, but also earlier feedback tools after analysis and elaboration and after synthesis, so you don't have to wait for the full flow to finish before you can get some useful information about the design. And then last, also like some better analysis tools, like a tool to look at multiple runs of your design at the same time. So in the next slides, I'll go over some examples of these improvements. So first, let's look at QOR, or quality of results improvements, that we've made over the past 5 years. I'm talking here about Fmax, compile time, and peak memory. These charts show the ratio of improvement that we've achieved over the past 5 years. So on the left, you see the Fmax improvements. The black line is the Agilex family, and the blue line is the StratExtend family. And you can see that we achieved a 37% Fmax improvement on Agilex devices, and that's worth about 2 speed grades. So that's a super significant improvement. And then for StratExtend, we also improved it by 14% over the past 5 years, which is about 1 speed grade worth. So these improvements, there's some innovative algorithms that went into getting this, because that's actually a pretty big improvement. And Mahesh in the next talk will go into some more detail about what kind of algorithms we used here. So while we improved your Fmax significantly, we did actually also decrease the compile time for Agilex by 29% and StratExtend by 14%. And the peak memory also reduced by 33% for Agilex and 5% for StratExtend. And that allows you to basically compile the biggest design with 64 gigs of memory. So how do we measure these improvements? Well, we actually use a suite of customer designs. And we use this suite to measure, like, basically what's happening in our release to release, or really change to change that we make in the software. But we also use these customer designs to drive new improvements. So we will analyze like how the designs behave in our tool, and whether there are some things like maybe a bottleneck in the compile time that we can fix, or maybe some new ideas of how to improve the Fmax. So this example chart shows you the compile time ratio from one release to the next. So each bar here is one of the customer designs in the suite. And then like below 1 basically means the compile time improved. So you can see that most of the designs have an improved compile time here, on average about, like, let's say 8% improvement. But there's a big swing in like how much improvement all these designs get. So you can see on the left there's one got 40% improvement. But on the right there are a few that actually got a little bit worse. So yeah, this shows you that like all designs are not created equally, so they behave very differently in our tools. And so for us, it's really important that we have a really wide variety of customer designs to tune our tools on, because we want the tool to be better for everyone, not for a small class of customers. So that's why I'm asking you to please consider sharing your design with us, because then we can add it to our design suite, and we can actually tune our tools to your designs. So you might say, like, what's in it for me? I mean, I'm not really that comfortable sharing my IP. Well, what's in it for you is that you might see QOR improvements next time. You might be the design that gets maybe almost 50% compile time improvement next time. We will also, for a limited number of designs, we will provide you with recommendations on how to improve your design. Like maybe there's some RTL changes that you can make that would really help the timing, or maybe there's just some simple assignment adjustments. And we can also offer 1-year free license for Quartus Prime software and Intel Premium support. So any requirements? Yes. So we do want the design to take at least 65% of an Agilex device, because otherwise it's not as useful for us to tune our tools on. But then you can upload your design to a secure enclave on Azure, make sure that nothing gets leaked. And that's it. And try to be fast, because we don't offer all these nice goodies for everybody. So yeah, if you're interested in this, you can talk to me afterwards, or you can also talk to your FAE about this. So moving on to earlier analysis tools. We have a new schematic viewer we call the RTL Analyzer. And this is available. You can use this like right after analysis and elaboration is finished. So this is really early in the flow. So this, it has a lot more features than the previous tool, the schematic viewer. It's available earlier in the flow. It provides multiple snapshots to look at, and it loads faster too. So on the right, you see the compilation flow. Those 3 dots show the different snapshots that you can look at for the schematics viewer. The one on the left is the elaborated view. So this is right after we translate your Verilog VHDL to a netlist, shows the schematics of that netlist. So here, basically all the names in the schematic viewer should match the RTL. The last one is swept. So at the end of analysis and elaboration, we run an optimization step. It's basically the first optimization step that we run. It's called sweep, and it removes redundant logic. So that's like logic that's stuck at a constant, or logic that has no fan out, so it's not actually used in the design. And we propagate all of this across all the hierarchy boundaries to basically make the netlist as small as possible. So this swept view will show you the schematics after that first step. And then there's also the instrumented view, which is basically the elaborated view, but it adds on any system-level debug logic that was inserted. And then the constraint view, where you can also see the SDC constraints that were specified on the RTL applied to the netlist. So, like I said, there's a lot of new features in this RTL analyzer. One of them is the constraint viewer. So, in the past, like basically when you set your assignments and your SDC constraints, sometimes it's not really easy to see whether you set it on the right nodes and whether it's really working until you completed the full flow. So now with this constraint viewer, you can go in the RTL analyzer and you can see if your assignments are actually set on the right nodes. So you can filter by the different types of constraints, global constraints, instance assignments, source assignments, and also SDC constraints. And then you can also filter by name. So here you see a bunch of implement as output of LCell assignments. And now you can click on one of these and it will actually show you all the objects in the netlist that this constraint applied to. So this will allow you to see that that's actually what you intended to do. And this also works for wildcard assignments. So it will actually show you what the wildcards are applying to. And then you can create a color set for this, and that means you can actually see it in the schematic viewer as well. And then the other way around, like if you're in the schematic viewer and you select some object, it will actually show you all the properties of that object. So in this case, for example, it's a net bus, a bus with like 58 nets in it. And you can see the source file that it came from and the line number. And then in the second tab, the constraints will actually show you all the assignments that apply to this object. So another tool that we built on top of the RTL analyzer is the sweep hints viewer. So in the synthesis team, we get a lot of questions from people who wrote a design and they ran synthesis, and like a big portion of the design optimized away, and they don't really understand what's going on. Because yeah, like it all looked right when they looked at it, but they can't figure out what caused it to optimize away. So typically, these kind of things happen because there's some connectivity issue in the design, like maybe the clock wasn't connected right in some of the hierarchies, maybe some signal name was mistyped, or some value got the wrong default value. So we wanted to make a tool that helps people debug these kind of connectivity issues. And so sweep, like I said, sweep runs at the end of analysis and elaboration and removes a lot of redundant logic. And so this is typically the step, like if there's some connectivity issue in the design, this is the step where a lot of that logic will optimize away. So we created the sweep hint viewer, which basically builds a database. We build a database of all the sweep operations that happen during this step. And not just like what happens. So for instance, like a register that gets removed because the data in was stuck at 0. But then we also store the relationship. So if this data in was stuck at 0, what other sweep operation caused this to be stuck? And then with this database, you have all the information to trace all this logic. So we built a GUI on top of that that allows you to easily use this data to find your cause of your removed logic. And then there's 2 reports that help you to navigate this better. The first one is the root cause report, and that one will show you all the sweep operations that happened because something in the design, not because some other thing swept away, but because in the design there was a certain constant maybe. And then it shows you for these, the root cause sweep operations, the ones that cause the most other logic to optimize away, because those are typically the ones that they have an issue. And then the second one is the removed hierarchies report. It shows all the hierarchies for which all the logic got removed during sweep. So I have a video now that kind of takes us from these reports into the sweep hints viewer to show you how you can use it to debug your issues. So we start with the compilation flow, and we go to the synthesis report, and we navigate to the analysis and elaboration stage. And here there's a report called Hierarchies Optimized Away During Sweep. So this will show all these hierarchies that lost all of their logic during the sweep step. So in this case, there's 4 different modules with a number of different instances. And the top one actually had 38 gates before sweep and 0 afterwards. So this can point you to hierarchies that have an issue. But then the second report, which I think is even more useful, is the top causes of logic optimized away during sweep. So this shows you all these sweep hints that cause a lot of other stuff to go away. So the first line, for instance, shows this WC0DIN, which is an input instance port on a hierarchy, and it was stuck at 0 because it was unconnected. And it cost 242,000 things to sweep away in the netlist. So that's definitely suspicious because that's a big number of things that got removed. So now you can right-click on this and locate it in the design file. And sometimes that's enough to find the issue with the design. In this case, it's actually pretty obvious what happened because this DIN connection was commented out. So I don't know who did that, but yeah, that definitely caused all these things to go away. It's not always that easy, and sometimes maybe that was an intentional change and you're wondering why it caused so much logic to go away. So then you can also locate this in the sweep hints viewer. And that loads the RTL analyzer and the sweep hints database. So here you can also see all of these root causes, not just the top 10, but all of them. And still this WC0DIN is at the top. So now you can right-click on this and then actually see all of these 242,000 sweep hints that were caused by this one. So this is a pretty long list of things that swept away. So that might be a little overwhelming, but it shows the object type, the hierarchy path, object name, the type of sweep that happened, and then like the instance type and the source location. And now if you're like not interested in seeing all of this logic, you can also filter it. So for example, let's say we're only interested in seeing the registers that got optimized away. So we select the DFFEs here, and then we're only interested in the ones that were actually stuck at a constant. So select that, and then you can update the filter. And now it shows only 74,000 objects that were optimized away. So it's still quite a lot. But now let's just find like a specific one that we're interested in. So this D in R0, which is stuck at 0 because the data import was stuck. So now we can see more information about this particular one. If you click on it, you can show the hint trace. And this first shows the root cause, which we already knew was this D in port that was stuck at 0. But it shows in the green line, it shows, oh, actually it looks blue. It shows the full trace of all of the sweep hints that caused this one to go away. So you can expand this path and look at the whole sequence of things that caused it to go away. And then you can also color this path and actually show it in the schematic viewer. And I think this is really helpful for you to see how your register was connected to this thing that caused it to optimize away. So on the left, you see that D in port that was stuck at 0. And then you see the whole sequence of registers that all swept away. And then the mux, and in the end, it caused this D in R0 to go away. So I'm hoping that you find this tool really useful to debug your connectivity issues in your design. So moving on to timing analysis, earlier timing analysis. So there's two parts to this. First, you can now specify your SDC constraints on the RTL. So traditionally, in Quartus, you had to specify your SDC constraints on the post-fit names. And that's not always convenient because, well, first of all, you have to kind of wait till post-fit to know what the names are. But second, there's names like hierarchy ports that are naturally like names that you want to set constraints on, but those are not available anymore post-fit because we flatten all the hierarchies. So with our SDC on RTL, you can now put your constraints on the RTL names, like the hierarchy ports. And then in the full flow, we make sure that these constraints remain valid by propagating them to neighboring nodes when a node optimizes away. So for instance, when the hierarchies get flattened, we make sure that the constraints on those ports go to neighboring nodes. So that makes it a lot easier to set your SDC constraints earlier in the flow. And then the second part is timing after synthesis. So you can now run the timing analysis tool at the end of synthesis. That means you don't have to wait for the full fitter to complete, and that saves a lot of runtime because synthesis only really takes about 20% of the total compile time. So this timing analysis after synthesis will not give you the full accurate timing because we didn't do place and route yet. Netlist optimizations haven't happened yet, so you don't have all the details yet. But it does usually show you like bigger issues that you might have in the design that will cause it to not meet timing later. So for example, you can do a logic depth analysis, which can show you the paths in the netlist that have a large number of logic levels. But you can also do a full timing report with estimated interconnect delays, and that typically also brings up the most problematic paths in the design. So another new tool that we have is the exploration dashboard. So this, like typically when you're doing your timing closure, at some point you're going to have multiple runs of the same design. Like maybe you ran multiple seeds and you kind of want to see what are really the problematic paths in my design. Or maybe you ran the design space explorer to try out different settings. So when you try to look at the different runs together of that same design, like you kind of have to open each one of them in its own quarters and then open multiple timing analyzers or chip planners side by side and try to compare things. It's a very tedious job. So we tried to make this easier with the exploration dashboard. And I should mention that this is a beta feature. So we would really appreciate your feedback on this and we will improve it more. Yeah, so with the exploration dashboard, you can create a workspace with multiple runs in it. And then it basically can generate aggregate reports across those runs. And it kind of summarizes what happens in all of the runs instead of you having to look at each one separately. And this is supported for many timing reports and hierarchy placement and design assistant. So here I have an example of the report timing that shows the top 100 failing paths for a workspace with 4 projects in it. So this shows actually each row in this report will show you a set of paths, really. And these paths can be in a different projects, but also like different bits of the same bus. So that kind of really summarizes where the critical paths are. So for each of these, it will show the minimum slack and the maximum slack across all these paths, and then the collection of from nodes and to nodes, launch and latch clock. And it also shows you how many of these paths were failing, how many in total were reported in this top 100, and then in how many of the runs we had failing, passing paths. So if you click on one of these, it will basically show you what you're used to normally in timing analysis. It will show you all of these paths. So I clicked on the second line, which had 138 paths, so they're all here, and 11 of them were failing. And from the first column, you can see that they were all the failing paths were actually in the same project. But other projects also had paths in the top 100. And now, like you normally do in TimeQuest, you can actually look at the details of these paths at the bottom, like the summary, the data arrival path, required path, and the statistics. So moving on to simulation. So simulation is something that you'll have to do at some point to make sure that your design is actually doing what it's supposed to be doing. So Altera doesn't have their own simulation tool, but we work together with Siemens, who provide world-class simulation tools. And Siemens has actually developed some tools targeted towards our FPGA called the Questa Intel FPGA Edition and Questa Intel FPGA Starter Edition. And when you have a Quartus, a no-cost license for Quartus, you get the Starter Edition for free. And when you have a paid license for Quartus, you get the full edition for free. That will be about like 4.5 times faster than the Starter Edition. So I have Kamlesh here from Siemens, who's going to tell us a little bit more about the Questa Sim and other tools that they provide.
All right. Thank you, Babette. By the way, my name is Kamlesh Mulchandani. I'm an applications engineer. I drive verification IP primarily in the North Americas region. And today I'm covering for one of our product managers who's not able to make it. So I hope I do a good job, but I'll also thank him when I go back. Thank you for that introduction. So Questa Sim is packaged with Quartus tools, right? It helps you verify your designs at several levels of abstractions with test benches, assertions, coverage metrics, etc. You also get waveform analysis to visually inspect the waveforms and also use that to compare with the reference waveforms that you may have, right? There is multi-language support. So I've seen in a couple of slides that Quartus Prime supports VHDL and Verilog output. They output those designs, right? Questa Sim also supports those languages along with System Verilog. Some of the IP companies have started using System Verilog as a design language. We also have a debugger, which is called Visualizer. It's far more advanced. It's capable of taking larger designs, more complex test bench, and also helps in productivity in debugging some of the advanced test bench related nodes. So if you guys need if you have a need for more complex, efficient debugger, or if you have a larger designs, more complex test benches, UVM-based test benches, there is a tool available called Visualizer that will help you do efficient debugging. All right, so I'm a verification IP application engineer, so I'm going to talk a little bit about this with a lot of excitement. Siemens acquired AV Design Systems earlier last year, March, actually, 2023. With that, we have an industry-leading portfolio for a lot of protocols and memory interfaces. So verification IP is natively System Verilog and UVM based. There is no C layer underneath. What does that mean? It results in a faster turnaround simulation time. And we have measured that against several other vendors that have verification IP solutions and also have a C layer underneath. So that takes a lot of time in case of simulation turnaround time. It's extremely easy to integrate, easy to use. We have received a lot of feedback from our customers, our users, time and again, that VIP is quite easy to use. And we also ensure that our VIPs are tested with our partner IP, design IP companies. What does that mean, right? We are not an IP company. So in order to be best in class, in order to provide a stable product, a best-in-class VIP solution, we work with leading-edge IP companies that partner with us so they can leverage our VIP and we leverage their IPs to ensure that we provide a best-in-class verification IP solution. Some of the examples of those protocols, PCIe Gen 6, Gen 7, CXL, UCIe. There is also a compliance test suite product available with verification IP that will help you save months of test writing. So the focus for engineers is not to write test cases and stabilize your test bench, rather use the CTS, which is a compliance test suite product, to focus more on RTL debug, find bugs, right? And we have seen time and again that our compliance test suite has found multiple IP bugs. We also have memory interfaces. I've seen a lot of memory mentioned earlier today. So DDR4, 5, 6, LP5. We are also engaged with a lot of customers on LP6, which is a new bleeding edge technology protocol that's coming up. GDDR6, GDDR7, DIMMs, in fact, even HBM. We will be hosting a webinar next month on HBM4 specifically. So we'll also announce some of the updates on that. We can share the links if you're interested in HBM. We'll be happy to have you attend those sessions. With the acquisition, we also not only acquired the verification IP, we also have a virtual in-circuit simulation flow. Now, what is that, right? It's like your in-circuit emulation, but we are actually using a virtual chemo model to bring up your firmware, right? We have seen a lot of times that firmware engineers typically wait for the chips to come back in the lab, and then they start bringing up their firmware or their software to ensure that the software and hardware are compatible. So with this acquisition, we have the solution already ready to be used actually at an RTL level. You don't need to wait for the chip to come back to your lab. You can actually use this solution during your RTL simulation time. So on the left side of the screen that you're looking at is a virtual platform that's an OS or your drivers or even a bare metal software, right? That connects with the simulation flow that has AV verification IP, your DUT. You can see a lot of interfaces that are available for this application, CXL, PCIe, Ethernet, NVMe, USB, to name a few, right? These are some of the examples. Now, what is the benefit of this, right? You want to left shift in your schedule. You don't want your firmware team to wait to bring up their software. What do we do with this application? It helps you bring your firmware at a stable point, right? So that your hardware and software can work together in the simulation board. So what are you really doing is you're augmenting the VICS solution, which is virtual in-circuit simulation, to your simulation bench, your simulation environment. So you have everything that you have, which is your IP, your test bench, your design that's simulating, that's your test bench flow. And then you connect that with this virtual in-circuit simulation using adapters that translates the system level, C level transactions to a system Verilog level interface. So that's the beauty of this. And what does that result in? It gives you an accelerated confidence in overall hardware and software readiness, right? You want your designs to be ready in both software and hardware as soon as possible. And now I'll pass it on.
Thank you. I think I have 2 seconds left. So my last topic, this is my last slide, faster debug with simulation. So when you do in-chip debug, in Quartus, you use signal tap. On the left side, it shows the flow that you go through. So you instrument some signals after elaboration, and then you run a full compile and you sample these, you run your design on the board, you sample these signals and analyze the waveform to get more insight in what your design is doing. And typically, you didn't get all the right signals, so you have to repeat this process. And there's only limited resources available, so you can't just add all the signals. So we have a way to speed this up with simulation-aware signal tap, where you basically enhance your captured data from a signal tap with a simulation of the RTL to give you more visibility of your design. So that's the flow that's shown on the right-hand side. So you instrument your signals again, but this time you use a simulation-aware node finder, and you can tell it which hierarchy in the design you're interested in to know more about, and it will automatically select a minimum set of nodes that need to be instrumented to make sure that you can run simulation and get all the visibility that you need. Then you run your full compile and you run the design on the board and you capture these signals. And then in SignalTap, you can generate the RTL test bench with these captured signals, and it also generates all the scripts that you need. And now you can run RTL simulation with this test bench and actually get the full visibility of all the nodes in your RTL from simulation. And so this requires fewer iterations to actually get the visibility that you need. So that concludes my talk. So I'm inviting you to install the latest and greatest version of Quartus Prime and try out some of these new ease-of-use features. And please give us feedback on those features, because ease-of-use features get better with multiple iterations of feedback. Also, please consider sharing your design. And these links, you'll also be able to get them from the video recording later, so don't worry too much about getting them now. And then back to Jeff.
Altera, accelerating innovators.